Alright, so now we're on to chapter 10, which has to do with sampling.
Don't you think the kids would enjoy a nice song with a melody?
What you got, Holmes?
It is a rare, one-of-a-kind original pressing.
Oh, yeah? All right, man, I'm gonna put it on there for you, all right?
Thanks.
So by this point, you should understand how to come up with a research question and the kinds of data that are going to be helpful in answering that research question. The next issue is who are you going to collect this data from? Now, to be clear, no researcher ever sets out with the intention of studying everyone, the entire population of the world. That's crazy, it's overwhelming, and it's impossible research. Instead, we define a specific population that we're going to be interested in studying. So let's say we're studying 5th grade students in Kansas, and we want to find out about their reading comprehension. Well, that's going to disqualify a huge number of people in the world from participating in our study. More than 99.99999% of the world's population isn't going to make the cut. So to put it another way, the population are the people that you want to apply the results of your study to. These are the people you want to describe. So do you think it would be possible or even practical to test every 5th grade student in Kansas on their reading comprehension? I mean, that would probably be the most accurate measurement of what's going on with 5th graders. That's called a census when you test everybody. And maybe it would work if I had like a large grant from the government or something. But if you're a poor grad student operating out of like a GTA office like this one here,
No food for you grad students till you grade 3,000 papers.
then chances are, even with the narrow population, you're still not going to be able to manage testing every 5th grade student. So when you're designing your research, keep this in mind. If your study is unmanageable, then you're not going to produce any results. Sometimes it's a matter of balancing what's optimal with what's actually practical to accomplish. Therefore, as researchers, what we do is we establish what's called a sampling frame. And the sampling frame specifies where you're collecting your sample from, i.e. the people that are actually going to be included in your study. Optimally, the population and the sampling frame should be identical. But as we said, this generally is not realistic in practice. Instead, it might be more realistic for me to test students within a 45-mile radius from Manhattan. So I might begin to develop my sampling frame by identifying all of the schools in the 45-mile radius. Even then, if I went out to every school and tested every 5th grader within that radius, it would still take forever to do the research. So the sampling frame only defines where we're collecting our sample from. So from all the students in all the schools within 45 miles from Manhattan, maybe I'll take a sample of 350 5th graders. And it's these 350 that I'll give my reading comprehension test to. So I'm going to claim that these 350 students are representative of all the 5th grade students in Kansas, and that there's no significant difference between them or anyone else. Ideally, what you want to see is that your sample lines up with the sampling frame, and the sampling frame lines up with the population. When you have this kind of alignment, you can state that your results are generalizable, which is the ultimate goal of quantitative research. But still, keep in mind, we're talking only about 5th grade students in Kansas, not everybody in the world. Of course, if you actually read quantitative research articles, you'll note that the authors themselves often disclose the limitations to the generalizability of their studies. They usually have a phrase near the end of the article that says something like, "Care should be taken when applying these results. The sample consisted only of Kansas and 5th grade students and may not reflect the results of other 5th grade students around the country." And then the researchers may give some reasons why 5th grade students in Kansas are unlike other 5th grade students and what sets them apart. So as I said, generalizability is the main goal of quantitative research. The representativeness of the sample to the population is a major key in producing valuable quantitative results. We want whatever we find in our study to be generalizable or applicable to the population. If our results are only true for the particular people that we studied and don't extend to the population, well, there's not really much value in knowing that. We want to select a sample from the population and then generalize to that same population. If we come at this from another direction, the text actually mentioned parameters and statistics. Now, a statistic is calculated from a sample. For instance, in our study we found that 68% of blondes do in fact have more fun.
A kiss on the hand may be quite continental, but diamonds are a girl's best friend.
A parameter, on the other hand, is the actual characteristic of a population. If your study is generalizable, then the statistics should be a close estimate of the parameter. However, we need to be aware that it is an estimate. And there is always some level of error involved in generalizing from a statistic to a parameter. In our study, we found that 68% of blondes have more fun, while in the population, the true number might be 65%. And it's just by simple random chance that we had a slightly higher proportion of fun-having blondes in our sample. Random chance always exists, and it always influences the results. As I said earlier, our job as researchers is to make the possibility of that error or random chance as small as possible.
I'm crushing your head! I'm crushing your head! I'm crushing your head! That's what I'm doing, flathead!
But you never really totally get rid of it. Truth equals results plus or minus error. Let's talk a little bit about sampling variance then. The text mentions something called repeated sampling, and a lot of students seem to get confused by this. To be clear, the repeated sampling is purely a theoretical concept. It's not something that any researcher actually does. Let's say we wanted to look at the average height of students in this class, and between the two sections there are about 70 students. Well, I could take a sample of, let's say, 10 to estimate the average of all 70, and maybe the average of that sample is 5'11". And then maybe I'll take a second sample from the 70, and I can do another measurement, and I can find out maybe they're only 5'8" on average. Well, I could do this over and over and over again, taking different samples. And each time I take a different sample, I'm going to get slightly different results because of sampling variance. That is, people are unique and they naturally differ from one another. Therefore, no single group is going to be the same as any other single group. But there's no point in doing this repeated sampling because mathematically, the average of all the combined averages is equal to the average of the whole. Therefore, it would make more sense to include everybody in a single sample of 20 instead of two samples of 10 and 10. In either case, we'll end up at an average of 5'9.5" for the sample statistic. Okay, so if all those numbers kind of threw you off a bit, the important thing to take away here is that a single sample of an adequate size is sufficient to estimate the parameter of a population. You don't need to subdivide it into smaller samples. So the question that generally comes up at this point is, well, what is a sufficient sample size? And that gets into kind of some deeper statistics that I'm not going to get really into here. But you can find sample size calculators online that can help you answer that question. So what I will say is that adequate sample size follows kind of a curve. As the population increases, the proportion of people needed to be included in the sample decreases. So for example, if I really wanted to estimate the height of 70 people, I need to sample 59 of them, or 84%. But if I wanted to estimate the height of 700 people, I'd only need to sample 248, which is actually 35%. And for 7,000, my sample size would only need to be 364, which is 0.052%. Therefore, if you have a really small population like 70, it makes more sense to do a census and just sample them all. Another thing that you might note, though, is that a larger sample tends to give you more statistical power. In other words, the more people you include in your sample, the less impact random chance will probably, meaning as a function of statistical probability, have on your results. And the higher probability that your sample statistic will be closer to the population parameter. So when you collect a sample, sometimes you have what is called an outlier. An outlier is someone whose data just doesn't fit the general pattern. So let's say we're looking at income and we have a sample of 2, which is obviously unrealistic, but this is sort of just to demonstrate a point. Person A has an income of $25,000 per year, and person B, who's the outlier, has a income of $2,500,000 per year.
If I had $1 million, we wouldn't have to walk to the store. If I had $1 million, we'd take a limousine 'cause it costs more. If I had $1 million, we wouldn't have to eat Kraft dinner.
But we would eat Kraft dinner.
We would eat lots of Kraft.
We would eat way more Kraft dinner than we eat now. Because you can afford to buy it by the case, by the crate.
I'd pay someone to make it for me, though.
Pay my parents to make it for me. They make it for me now, I just can't afford to pay them for it.
Therefore, the average of our sample is going to be 1,262,500. If we add a third person to the sample who's like a normal person, then let's say they make 28,000. The average of the 3-person sample is now 851,000. The thing I'm trying to demonstrate here is that as our sample size increases, the effect of an outlier on an average decreases. That large variance between the individual scores is offset by statistical power of the group. In other words, we're able to provide some control over the variance. However, if our sample size is not adequate, individual scores will have more impact on the average, and therefore the results will be less precise. However, there are cases when a score is so disproportional to the group average that it significantly distorts the findings. In these cases, that would limit the generalizability because what we find doesn't actually describe most of the people in the population.
Fooled by the rocks that I got. I'm still Jenny from the block. Used to have a little, now I have a lot. No matter where I go, I know where I came from.
So let's say that our average population income is somewhere around 27,000. In our sample of 3, the average was 851,000, which is quite a bit more than 27,000. The common practice in these cases is to throw out the outlier data. When we remove Mr. 2.5 million from our sample, then what we're left with is a average of 26,500, which is much closer to 27,000 than 851,000 was. Okay, so repeat after me. Generalizability is not universality. Generalizability is not universality. Generalizability is not universality. This is very important to understand. It's another mantra that researchers should recite to themselves. In quantitative research, what we're investigating is broad general trends in a population. What we're saying is that what we've found in our sample describes roughly most of the people most of the time. What we are not saying is that our findings describe all people all of the time. We need to remember that we're working with aggregate numbers. We can discover what the average income of a population is, but we can't accurately predict what any single person's individual income will be. In this graphic, you can see the trend line in blue, which describes the overall path of the stock prices, and it's generally an upward trend. But as you see, the trend line very rarely actually matches any of the prices. At any given point in time, they actually fluctuate pretty wildly up and down. So this is also important to consider when we're thinking about the push for evidence-based practices. You know, of course we want to do what's been demonstrated to be effective for most people most of the time, right? But we also need to be aware that in some cases, inevitably, evidence-based practices are going to fall short. We need to have the flexibility to adapt in those circumstances in order to do what's right for the individual, regardless of what's been demonstrated to work for the masses.
The wonderful thing about figures, it's figures are wonderful things. The tops are made out of rubber, the bottoms are made out of strings. The bouncy, flouncy, flouncy, pouncy, fun, 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 fun. But the most wonderful thing about figures is I'm the only one. I'm the only one.
So let's talk a little bit about sampling methods. First and foremost, we have random sampling, and this is the gold standard of quantitative research, in which everyone in your sampling frame has an equal probability of being selected for the study. If you have a large enough sample size and working from probability, this is the best way to ensure that your sample is representative of the sampling frame and hopefully, the population. Now, when I was your age, when I took this course back in the day, my professor gave us an assignment to generate a random sample of 100 names from a local phone book. Tedious does not even begin to describe it. Fortunately for you, there are computerized databases and random number generators and things that make doing this work a lot less tedious. You still need to compile a list of everybody who could potentially be in your study, but the selection process is much easier. Now, a lot of people seem to be thrown off by cluster sampling. It's really pretty simple though. Cluster sampling is basically random sampling, except instead of sampling individual people, you're sampling groups. So, remember the previous example we were talking about, the 5th graders from Kansas? It's possible I could pick, one student here, one student there, one student there. And I could build up my sample that way. But then I'd spend all my time driving around to all these different schools sampling just 1 or 2 children. It would be much more efficient for me to sample a school and then test all of the 5th graders at that school. The school is a cluster of participants. If you're doing 2-stage cluster sampling, you would first randomly sample a school, then you would randomly sample students within that school. So I might decide I want to get 35 students from that school. So just a tip for you quantitative researchers, you usually want to have a greater number of participants than you actually need for the study, because people often decline to participate or they'll drop out in the middle of the study or something else might happen. So then you've got a backup for those situations. This is especially true in survey research with a typically pretty low response rate. So let's talk about volunteer bias. An issue with this, and one that's unavoidable, is that not everyone always has an equal chance of participating in your study, even using random sampling techniques. They need to consent to participate, and not everybody is going to consent. You're not going to get data from people who decline to participate. And so in some way that might affect the representativeness of your study. Let's look at TEVALs, teaching evaluations, as an example. Now, it's common practice for students to evaluate the instructor at the end of the semester. We all know that. Unfortunately, these evaluations often suffer from very extreme volunteer bias. Let's say the professor is teaching Psych 101 and has a large lecture hall of like 200, 300 students. At the end of the semester, TEVALs are emailed out to all of the students, but realistically, most of the students are probably going to blow it off. It's only the ones who have particularly strong feelings about the course who are going to be invested in filling out the survey. So maybe they've been frustrated all semester, and this is their chance to get payback and tell the prof exactly what they thought of them in their stupid course,
The next screw that falls out is going to be you.
Eat my shorts.
What was that?
Eat my shorts.
Or maybe they really enjoyed the course and they found it deeply stimulating and they want to show their appreciation, so they're going to fill out the survey and say nice things, get positive feedback.
Captain, my captain.
Sit down, Mr. Anderson.
But for those who found the course to be just merely adequate, could be the majority of them, they're less likely to be motivated to complete the evaluation. And so what you end up with is a very distorted picture of how the class responded to the professor. You know, and you see the same thing happening in political opinion polls and commentary on the media as well. You know, the extreme people on the left or right, doesn't really matter, who are the most passionate and the most animated about the whatever causes they're talking about, they seem to get the most airtime. I believe that most Americans or Canadians or whoever, you know, we probably have some opinions about politics, but we're generally fairly moderate in our opinions, and therefore we're kind of boring. And we're less interested in going out and making our voice heard, and therefore we're going to be less represented by the media. However, if we believe what we see on TV or, you know, see online, then the country is very deeply divided, and the people on the opposite side of us, they come off as these raving lunatics, and we also tend to be more tolerant of our own raving lunatics. But I believe that the reality is that most of us are far more moderate and measured than is portrayed in the media.
Telling you, the government has a car that runs on water, man. They just don't want us to know, because then we'd buy all the water. Then there'd be nothing left to drink but beer. And the government knows that beer will set us free.
What if we lived in a perfect research world where everything we were supposed to do as researchers was actually possible? What a world that would be. Unfortunately, it doesn't really work out that way in real life. Random sampling is the ideal that we should strive towards, but in many cases it's not possible. Instead, most research done in education is done with convenience samples. Why? Well, because they're accessible. They're convenient. It's a hassle to go out into the actual world and round up a bunch of random participants who represent the population, you know, that we're studying. However, if you can make a convincing argument that the people you have access to are not significantly different from the larger population, or at least acknowledge that as a limitation of your study, you can possibly learn something from a convenient sample. And this is why psychology students in introductory courses may be some of the most researched and best understood populations on the planet. We know more about Psych 101 students than anybody else. Academics, particularly psychologists conducting research, have easy access to them, and they're often willing to participate for nothing more than extra credits, so that's great. In some rare circumstances, you might find a need for stratified sampling. I'm trying to think. I haven't come across it too often in research articles, but it exists, and it's happened sometimes. If there's a particular variable in your study that you need to carefully control for, so like income levels, right, or you have a small sample size, you might need to use stratification just to balance out the numbers of participants in each stratum. In some cases, this is done because the sampling frame may not accurately represent the population, and so they need to ensure that the proportions of people included in the study represent that population parameter. And that's to avoid having certain characteristics overrepresented or underrepresented. In other cases, they may want to equate groups that are not equivalent in the population. So let's say, for example, I wanted to compare the 1% with the 99%, in terms of wealth. Clearly, there are not so many 1%ers out there. If I went out and just did a simple random sample of 1,000, let's say, I would have far, far fewer 1%ers compared to the 99%ers. So doing a stratified sample, I would put a quota saying that I would like to have equal numbers of 1%ers and 99%ers, so that I could compare those groups. However, it's important to keep in mind that anytime that you're not using a random sampling technique, you're introducing a greater potential for bias and error into your study because you're interfering with the sampling. Since random sampling relies on probability, it's the best way to ensure the proportions of all variables that exist in a population are represented in roughly the same amounts in a sample of sufficient size. Okay, so we're going to come back to this concept in the next module. I'm just going to introduce it here really quickly, give it to you in a nutshell. We're talking about random assignment as sort of the counterpart to random selection. Random assignment is about splitting your sample into groups so that you can compare the two groups. Like random selection, it also relies on the laws of probability to ensure that your groups are roughly equivalent and the distribution of variables is roughly even. So, for example, the number of tall people in one group will be balanced by the number of tall people in another group. The number of smart people in one group will be equivalent to the number of smart people in the other group as well. So when the groups are balanced, all the extraneous variables cancel each other out.
The universe works on a math equation that never even ever really even is in it, and infinite spirals out creation wrong with 50 bit stones, and it is saying, well, we ain't sure where you stand. You ain't machines and you ain't land, and the plants and the animals, they are land, and the plants and the animals eat each other.
And therefore, any observed difference in the dependent variable after a treatment is applied to one group must be due to that treatment variable rather than, any of the extraneous variables. Like I said, we're going to come back to that in the next module, and we'll get a little bit more into detail on that.